Hi, I'm Nathan Sheely, and this is my final project for CSCI E-93 Computer Architecture. This is my architecture that I call November Twister. November Twister I describe as a almost RISC architecture. It is 16 bits. It has 16 general purpose registers in a register file. It has 3 special purpose registers that are not directly addressable, a program counter, an instruction register, and a processor status word. The memory system is both word and byte addressable, and my special feature is an instruction cache. We'll get into this a little more soon, but to get an idea of how this works, I have this program counter that holds the address of the next instruction for the running program, starting at 0. It will then fetch from that address from memory the instruction that will load into the instruction register. Those first 4 bits in the instruction are the opcode that will go off to a sequencer, which has its own sequence of states, and each one configures all these blue lines to set all these different components to be in the right configuration for whatever operation we're performing or sequence of states for the operation. So to get an idea of the clocking scheme, on each falling edge, the finite state machine will advance to its next state in the sequencer, configuring the data path. Signals in the data path will propagate through the system, and on the rising edge, we'll do any write-backs to any registers or memory or anywhere we need. As I said, there are 16 registers in my register file. They are all addressable by these encodings. In the assembler, you can call them by their number or their name. They all have their own convention on how to use that is not strictly followed, except for register 0, which is enforced of always being the value 0. You can read to it, write to it, whatever. It's always going to hold to 0. It has 11 different opcodes that set bits based off these 6 different instruction types. I have my ALU operations, which select 2 registers from the register file, takes those values, performs the ALU operation on them, and writes back the result. An immediate, instead of the lower 4 bits addressing in the register file, it's just 4 immediate bits as the argument. Loading, storing words and bytes. We select the register files for the address and the value. Feeds back to the memory subsystem, and in the case of a write, it'll write it back into the appropriate register. Branching and jumping. For branching, if it's true, it'll select, the sequencer will actually select between writing back the increment for the program counter or the increment with the offset of the branch instruction. Jumping, it's the offset. And we can also jump off a register, which will just write, it'll select a value from a register, and it'll just write it right back into the program counter for whatever value is stored there. I support these ALU operations: adding, subtracting, shifting left and right, logical and arithmetic, and these logical operations. Multiplication has not been implemented quite yet, but as you can see, all these take 2 registers as their arguments. The first selected register from the register file is both the first operand and the result it writes back to. The second one is just the second argument. Now, as I mentioned, I also support immediate operations, or I like to call it the little nibble that could, because it's just 4 bits as the second operand. Seems kind of small, but there's quite a bit that's actually useful for. With adding and subtracting, you can do that by 1 and 2 to, if you want to loop over a sequence of bytes or a sequence of words. Shifting, 4 bits is all you need to get the entire 16 register width of shifting left and right. And for add or XOR, if you have anything that's sending off signals that's being set to those lower 4 bits that maybe you want to mask, it's useful for that as well. Now, I support branching using a processor status word. This is the part that's not really RISC because I'm holding state over multiple instructions. So I have an ALU operation that sets these different bits in the processor status word that is then used for following branching instructions on whether to evaluate true and go to the offset of the label in the instruction or just fall through. My assembler also supports these pseudo instructions. So I have moving to just copy the contents of one register to another, clearing sets the register to 0, pushing and popping for stack operations. The main thing I wanted out of this is this load immediate instruction. To make it in a single instruction, I can load an entire 16-bit immediate. So which is the instructions I had. That wasn't possible. So what this does, it allows you to write in the assembly language a 16-bit immediate, and the assembler will split that up into the appropriate load upper and load lower immediate instructions in order to get that whole value into a register. Another thing I really wanted out of this is to make it so I can make the argument be a label. So in my assembly, I can write a label and store it into a register. This kind of creates an idiom where when I make a subsystem call, I will save the return address as a label. So I can run the subsystem and then it'll come back to if I have a label out where I was, back where I was, or I can jump to any other part of the system as the return from a subsystem call. So I wrote an assembler and an emulator for my assembly language, all written in C. The emulator will run a program that has been assembled by the assembler. And we run it. You can see it features showing all the different registers, and it will disassemble the current program counter, the value for that program counter, and it'll give you the hex and the disassembled result. I can type H and get a help menu to see all the different things it can do. I can step through the system, which will highlight any changed registers. I can also set a breakpoint where I have my listing file generated by the assembler and I can see what instructions are at what points. So I set a breakpoint at 3E, which I know is right after it reads in the first number for my multiply program. So we set the breakpoint, hit it, and now we can step through and you can see the assembly is loading in the address to store the resulting value. So I loaded the address, which was a label originally for where in data I wanted to store this. I have the address of where that data buffer essentially is. And now I can store the value of R5, which is C, which is that 12 I entered, into that memory address. So if I step one more time, I stored the word, and now we can look in memory at the address 41A and see the value C. Okay, so this is the DE2115 board. You can see my computer is loaded up in the FPGA with a test program. We can reset. So we have various controls here. We've got a memory hold, a clock hold, a cache enable. All these 5 set different debugging settings for these displays. So displays you have here, it shows a code for the sequencer, so what state the sequencer is currently in. This is just an identifier for what register or data line is being shown in these 16 bits. So right now it's the program counter. We'll let this run for a little bit. You'll see we're now at step 17A. We can also see the contents, look at the instruction register. You can also step through all the different registers and see what's currently in them. In addition to that, we can also see what's in the register files, or when register files are held high. We got a clock divide, so we can step this all the way down, reset. We can see it's stepping through very slowly. We slowly bring that clock up, all the way up to full speed. Now we can also step through the states in the sequencer. And as you can see, we have all these different LEDs for data about the state of the processor.
We got memory suspend if the clock hold as cache enables up. We also got this one, L8414 for if we have a cache hit. We have these lower ones to say like for the memory subsystem if an address is ready or the data is ready or if we're reading or writing. And down here we have the processor status word flags. Those will light up if we have a 0, negative, or carry, and you'll see those light up as we go. So they blipped. Thank you.
All right, so this is the multiply program running on the hardware. We can see this is talking over the serial bus to a terminal emulator on my PC. This my usual test program for timing is just 12 times 34 to get the result. This can support the full range of multiplication that can fit in a 16-bit signed integer. So we can also support larger numbers and negatives as well. So the performance has not been what I expected. So that drove me to make my special feature a instruction cache, which I thought would be the quickest, easiest, just bang for my buck way to improve performance. It's a direct map instruction cache. So what that means is I'm just caching instructions. I have 1 kilobyte. So every instruction I did have a fetch from memory in order to get its value. With this, I don't have to do that fetch from memory if I've seen that instruction before. Um, the way it works is I take because it's 1K, the lower 10 bits, not quite, it's the lowest bit's always going to be 0 because the instructions are word aligned. So it's the next 10 bits up is the index into the cache. And then in that index, I have a tag of the upper 5 bits that are left. So whenever there's a read, um, it checks if it's an instruction, and if it is, it'll check this cache. If those middle 10 bits pulls in the index and checks the tag if the instruction has been read before and if it's good. If it is, then it's a hit, and we don't have to talk to the memory subsystem. We can just take the data directly from the cache, and we are good to go. All right, so this is the real motivation for that cache. The first time I got my computer working in hardware, I ran that multiply test program, and it took 48 seconds from initiating the program through taking in the values and producing the result of 12 times 34. That's set off some alarm bells. That's far too long. So I start off with cache. The first one I made was kind of a form, fit, and function replacement for the memory unit. So it just acted as a middleman, retaining the exact same interface. This was a terrible idea because now the sequencer is still going through the same steps it was before. And I needed to simulate all the signals the memory subsystem was sending out, even when it was just a hit from the cache. So this did cut out writing to the memory subsystem when there's a hit, but there's a lot of clock cycles that I'm still going through for these instructions that were really unnecessary. From there, I went on to just cleaning up my sequencer because I noticed there were some states that could be consolidated and that provided an improvement, fewer clock cycles for those instructions. And then I went back to the cache, um, forget the whole form function fit. I added signals to tell the sequencer when there's a hit. So the moment it does a fetch, it can see there's a hit and go directly to the decode, skipping over all the other stages for reading and writing to the memory subsystem. And that was, at least percent-wise, the kind of performance boost I was expecting. From there, I noticed the code I wrote, it's a lot of subroutines and nested subroutines, which is not performant. So I cleaned it up just a little bit and I immediately got this huge performance boost. So it's not where I want yet. There's a lot of improvement that can still be made, adding a data cache, more code cleanup, playing with the clocking scheme, lots of stuff. But this was 3.7 times faster is still a huge win. All right, so another test program I made to evaluate on the system was Fibonacci computing. The last test I performed without the cache enabled, it took 55 seconds to compute fib of 21, and with the cache, it took 19 seconds. The last demo I want to show off is really just dead simple. It's echoing, but most of these programs have been talking over the serial line along the top. I wanted to show off being able to communicate with the PS2 input. So this keyboard is plugged directly into the board, and I can type off and see the results in PuTTY. Thank you for your time. I hope you enjoyed the presentation.